Yeah. So given a curve, right, and this viewed as an orbit of some moving object in the space. It's three-dimensional space. Okay. So suppose we have this curve, right, and we want to do two things. One is how to measure the length of this curve. Okay. Then how to tell at some particular point the so-called curvature of the curve at that particular point. That tells you how curve of that curve at that point. Okay. And you cannot say, oh, it's very curved. You know, you have to take a quantity to describe it. Okay. So let's talk about the length of the curve. The length. Okay. Okay. The length. First of all, yeah, we find we call so-called parametrization. We assume that the curve C is a vector equation, so that R of T is going to be a vector equation for the entire curve C. So that means have a starting point, and this is point Q and P, and at point A, this is P, point B, and this point Q. Okay, so T here is between A and B. So you have a vector function, okay, which serves as a vector equation, okay, for the curve. Okay, then for every T, you have a tangent vector, right? Okay. And so the length of the tangent vector, right, is going to be, yeah, it can be not necessarily to be unit. Okay, so this is the length of the tangent vector. Okay, the length of the tangent vector. Okay. And we have the formula for the length of the curve. So the length of the curve, which sometimes is just simply denoted by LC, okay, is given by this integral of this function. Okay. We can prove that, and the proof is not difficult, but using calculus. Okay.
Could you just verify what the formula is? What's the formula? I can't read it.
Oh, the formula is the integral of the length of the. I can use the one. Okay, I can use just only one bar. Okay, so it's not necessary to use a double vertical lines. Okay, this is the length of the tangent vector at time t, and then this becomes a function of t. So we can integrate the function. Okay, and we can show that this is an independent. And this is well defined. So if we have another vector equation for the C, okay, you will get the same integral. Okay, so the value of the integral is the same. So I have to make a couple points to explain this formula. Okay, this is a formula. It's not a definition. We derive this formula using calculus idea. Okay, the idea is that, okay, it's not given in the book, but I'm trying to briefly give you that. Okay, so you take a partition. Okay, then you have a bunch of points here around this, right? So if the gap between ti and ti plus 1 is small, then the corresponding points, the gap between corresponding points is also small. So so the length is almost equal to the sum I from 1 to k. And yeah, this is so how can I measure the distance between the 2 points? I use line segments instead of curve, okay, to measure the distance. The distance between 2 points, ti minus 1 r to the ti, okay? So the distance between those two will be ti minus 1, okay? And then add them together, you actually get the length of this special curve consists of line segments, but very close to the original curve, right? And then you divide by delta ti. Okay. Now what is delta ti here? Delta ti is just ti minus 1. Okay. So there's the difference of these two endpoints. Okay. The point here's the one in the middle. Actually, you can show that in mathematics, okay, called the mean value theorem, is equal to the derivative of another point. Let's call it ti star. Okay, and then delta ti. Now, what is ti star? This is a ti minus 1 ti. So there's a point called ti star somewhere, such that this quotient is going to be the derivative, the value of the derivative of that point. Okay, so then you take the limit, and let n goes to infinity, and also this ti goes to 0, delta ti goes in. So then the sum, okay, the Riemann sum, okay, has a limit. That limit is actually denoted by this integral. Okay, so this is how do we get the formula using calculus idea. Okay. In the book, it's not mentioned. Okay. Okay. All right, so we use this formula. I have to make a couple points. See, based on this definition, based on this formula, I see that if r tilde and if r tilde and tau tilde, this is a t tilde, okay? This is another vector, is another vector equation for the same C. T tilde is written A tilde and B tilde, okay? Then the formula tells us this will be the same integral, okay? So it doesn't matter what vector equation you use for the curve. The integral will be the same value. Okay, so if I give you a curve and different students find a different parametrization, yeah, we call it the vector equation the parametrization, and then you end up with so it gives you the same length. So here's an example. Let's take a look at the example, okay? And I'm going to find I'm going to some nice example here. Right, two-dimensional, okay. Right, so here's a curve C given the curve C, okay, C. Okay. And given this curve C, which is described by the following, it's two, let me use RT, okay. So this is going to be cosine 2t, sine 2t, and yeah, we can do the 3t, okay, and the 4t, okay. So t is between 0 and 2 pi. So the curve, okay, is going to be like that. This is a starting point, and then rotate to the same point, okay? So we want to find the length of this curve, okay, in the space. So when t equals 2 pi, I will get 0, get 1, 0, and 8 pi. And here,
What is
1, 0, 0, okay? So this
what
is
is
my p,
z equal there? Is
that's
that
my q,
14?
okay?
8 pi.
What does z equal? Is that 14? Just confirming.
What is z? 40, yeah.
14.
Yeah. Okay. This is a helix, okay? We call it helix. Okay. So now, okay, let's figure out, yeah, let's find the length, okay? So what you do is you find the x at r prime t. So you get -2 sine 2t. Oh, this 3, okay, -3. And then 3 cosine 3t and 4, okay? And then the length, okay, of a vector is going to be the square root of the square of each component. So that will be -3 sine 3t squared, 3 cosine 3t squared, plus 4 squared. Okay. Okay. So I simplified. It is going to be 3 squared, so 3 squared, and 4 squared. You know why I choose 3 and 4 here. Okay.
Hey, Professor,
Yeah.
do you mind going through those steps? We had a similar problem on the last class, and do you mind doing the steps for that simplification, please?
Simplification. Oh, how did I get a 3 squared?
Yeah.
Oh.
Because I know that sine of
Yeah. So
x plus cosine of x equals 1, right? But where do the 3s?
This is okay. Yeah. When you square it, you get 3 squared sine 3. Okay. And here 3 squared cosine square 3t, then 4 square. Okay. Then the sine square cosine square is going to be 1. Add them together. Okay. You take 3 square out. Then, see? And this part, it is going to be 1. Doesn't matter what is 3t or 4t, 5t there. Okay. It's independent of the angle. So that's why I get 3 square plus 4 square. And this is a 5 square, 25. So that's why it's just 5. Okay. So it's constant. So the tangent vector has constant length. And also, if it's a moving object, if the vector equation describes the moving object, the position of the moving object, that means this velocity has a constant length, so the speed is constant. It's moving at a constant speed along this orbit. Okay, so now what I'm going to do, okay, so according to the above formula, it is going to be the integral from 0 to 2 pi, right? You write down this formula, okay? And then you will get, since it's a constant, so then don't worry about the integral, okay? So it's going to be just 5 times 2 pi, it's 10 pi, so the length is 10 pi. 10 pi, of course, is longer than 8 pi, so the height from P to Q, right? The height is 8 pi. And then, so the length of the curve should be larger than 8 pi, right? In the space, the strict line has shorter distance. So when you look at the get answer, you just check whether this makes sense or not. If you get a number less than 8 pi, something's wrong, have to go back, okay? Because the length of this curve C should be larger than the distance between P and Q, because P and Q is a strict, this is a strict line, and the length of this strict line is equal to 8 pi, okay? So I think this is the correct answer. Now, for the same curve, okay, there's another way to describe. Okay, so how can I? We try. Here's another one. Okay, so let R tilde, okay, to be R tilde T tilde. I'm going to describe the sine. This is cosine, okay? This, and the cosine 3 over 5t, okay? And the sine 3 over 5t. I just divide by, here's a 4 over 5t, okay? And divide each t by 5, okay? Now, in order to get, this is t tilde, okay? Okay, so in order to get a complete curve, T tilde, okay, is actually going to be it's between so it's going to be 5t, okay. So basically, I let T tilde to be 5t, okay. Then T tilde is between 0 and 10 pi, okay. Okay, so then you get, when t equals 0, you still get the same point P, and when this is going to be 0, it's going to still point P. It's a 1, 0, 0. When it's a 10 pi, it's still Q, and that is going to be 1, 0, 10, right? It's 8 pi, okay? It's the same point. Okay, so this is another vector equation called the parametrization, okay? That is for the same curve, okay? Now, if T tilde is still viewed as a time, then this this moving object, okay, moves maybe slower than the previous one, okay? Because take a longer time, okay, to reach to the point Q, okay? So let's look at the derivative. Okay, when I differentiate, I get negative 3 over 5 sine 3 over 5 t tilde, and I get 3 over 5 cosine 3 over 5 t tilde, and 4 over 5, okay, right? Yeah, differentiate by the chain rule. Then you are surprised, and the length is actually going to be 1. So when you square it, okay, and you put something here, right? It really doesn't matter what is the angle, square, and 3 over 5, and cosine some angle here, square, and 4 over 5 square, okay? So for the same reason, sine square per sine cosine square is 1. So you only have a 3 over 5 square here, and you have a 4 over 5 square here, okay? And then add them together, that is going to be 1. Okay, 3 squared plus 4 squared, 5 squared, so that cancels out. It's a square 1, it's 1. Okay, so this one has a constant unit tangent vector. Okay, and this vector equation describes the same curve. Okay, and if you want to find using this formula, this vector equation to find the length, and this is integral from 0, T2 that's from 0 to 10 pi, right? and RT. Okay, use a new parameter T, and you find out you end up with the same result. Okay, and pi. So really doesn't matter which parameter you use. Okay, this is about. Then you say, oh, so good to tutor. Maybe can we always find such a parametrization for the curve? It's theoretically it's possible, okay? And let's try, okay? I did that, right? But maybe how about for general curve? So given curve here still, right? And then first of all, you have this is origin, and you have an arbitrary parametrization for the curve C. So this is the equation, okay? So here, A t equals A when t equals B is here, okay? But in general, this is not going to be, the tangent vector does not have a unit length, okay? But can we find another parametrization so that, yeah, I'm going to use another T tilde. Can we find another one, okay, for the same curve, so that can we find another one? Let's still use R tilde, okay, and this time I'm going to use the T tilde, use the S, okay, keep it, yeah. So for C, such that it's always going to be 1, okay, and that's possible. Why? Because imagine from physics point of view, it's already possible. Why? You just drive along this orbit at a constant speed, okay? And maybe just 1 mile per hour, or if you use this unit, right? Then you already find it, okay? Right? So first of all, this is orbit of a moving object at a different, at the various speed, right? From this point P to Q that describes that, gives you any moving object from P to Q gives you a parametrization for this curve. Okay, it's as long as the orbit is the same orbit. Okay, then you just set the constant speed. Okay, and set to be the 1. Okay, when some like a 1 miles per hour, I know 1 meter per second, doesn't matter, just 1. And then, okay, then that moving object gives you the parametrization such that the length of the tangent vector is always equal to 1. Okay, because the tangent vector is a speed, is a velocity of the moving object. Okay, so but for mathematics, how can I do that? Okay, I'm not given some information. Already have a parametrization. Okay, R over T. Okay, and what I'm going to do is I measure the length from here to here called S. Okay, and at the point T, R over T. Okay, so how can I find the relationship between S and T? The relationship between S of T, according to my formula, okay, it's going to be the integral from A to T. And that would be the derivative, right? So so to be not can be confused with the term notation, let's use a tau here, d tau, okay? The parameter, you can choose always choose different parameter, okay? So that tells you the length, that gives you the length of this portion of the curve, okay? The length of the portion of the C from P to R over T, okay? Right. Now, so S is a function of T because when T changes, S changes. Okay. So S actually is a function of T. Okay. And sometimes you can write S of T. Okay. This depends on it. Depends on time T. And since it's a function of T, so you can differentiate, right? According to the fundamental theorem of calculus, this is nothing but this, okay? So the derivative of the S with respect to T is just the length of the tangent vector. Okay. Now, I'm going to denote, okay? I'm going to denote this particular point by another vector which depends on S, okay? So I'm not going to use R2, right? I'm going to denote this one from here to here, and this vector denoted by tau S, okay? Yes, right? Then I get a new parametrization, okay? Okay. Then, yeah, so we define to be R over T, okay? And where S and T are related by the above equation, okay? Where S is going to be integral from A to T, okay? All right, so this one gives you the, yeah. So now let's find out the derivative. What is that, okay? So derivative is the derivative of R2 dot ds, right? Okay, and then use a chain rule, so dr, right? You're going to differentiate. Now, actually, t can be viewed as a function of s. If, yeah, by the chain rule, this is going to be, how can I do that? Okay, so actually, you can get this is d over t and the ds of dt. Okay. Yeah, that is a, that actually comes from the chain rule. Okay. Okay. So this is nothing but that's a relationship. Okay. All right. And now, yeah, roughly speaking, is like a dr of dt and ds of dt. That's going to be dr of ds, something like that. Okay. But for this one is I use I use a different letters. Okay. I just R2 that. Okay. This is channel actually. Okay. Now, okay, so you have this identity. So the length is going to be this dsdt. But dsdt, we already know that it is going to be the length of the tangent vector, the particular point. That's always equal to 1. Right? All right. In the book, for the convenience, so we do not, for the sake of convenience, we do not use R2. We just change the parameter. Okay, so it's up to us whether we want to use the R2 or still use the same R, but it change the parameter T. Okay, so this is let me check if there's any different notation here. So okay, so let me mention that. See, S is a function of T, right? So ds is S prime, so actually is equals this, right? Then since this is a positive, so T can be the inverse, you can solve for t in terms of s. So, right? Yeah. And then then dt over ds, right? You can differentiate t with respect to s. So t, yeah, you solve for t in terms of s, you get the inverse function. Okay. So this one is 1 over ds dt. So it's going to be can be written in this form. Okay, if we want. And then since t, then you say, well, this should be expressed as a function of t. Yes, you can do it like that. And what is s? What is t? T is a function of s. Okay. Okay. And for the same function, right? Since t is a function of t, so you can also express it like this. And this is in my notation denoted by is. Okay, denoted by. I use R2. Okay, R2 is a composite of two functions. All right, so those are the notations we get. Anyway, so the S is arc length, okay, and this called the parametrization of the curve with respect to the arc length. Okay, so R theta, okay, is called a parametrization. Actually, the parametrization. Okay, that's only one there. Parametrization with respect to arc length. Right? This is the ideal situation, and we should able to, for any curve, we should able to find the parametrization with respect to the arc length. But in reality, it's almost impossible to use the elementary function to describe it. Now, for the helix, I did it. Okay, for the helix, I did it, and but for an arbitrary curve, even looks very nice. It's almost impossible to express the parametrization with respect to arc length using elementary function. So let's take a look at this helix again. It's going to be cosine 3t, sine 3t, and 4t, okay? Right? Now, as I told you, this is not going to be, this is does not have a unit velocity, okay? Okay, but r prime t is going to be negative sine 3t and 3 cosine 3t and 4, right? But since the length is constant, so let's try to find out, yeah, this is a rotate, okay? Okay. This is how do I do it? Okay. That's the wrong picture. I'm going to redraw it. Yeah. So it's rotate like this. Okay. Coming back to the point, same location but above that. All right. So I'm going to find the arc length function. Okay. The arc length function. So from here to here, that's called the S. Okay. And that point T. So I want to find the relation between S and T. Yeah. All right. So here it is. Okay. So the length, this is going to be 3 here. The length is going to be 5. We already calculated. I'm not going to do it. Okay. So this is a constant. So S is going to be from integral from 0 to T R prime tau d tau. Okay. So this is a constant. And the answer is just 5t. So S, okay, sorry, I have to open the file. Yeah, it's back. Oh, it's gone now. Okay, this is 3.
Shouldn't be the first derivative. Should be minus 3 times sine.
Yeah. Okay. Where's my tool? Hold on. Give me 1 minute. Give me 1 second. I don't know what happened. Okay, so you differentiate, yeah, it's a negative 3 sine 3t. Okay. Then you get to t equals s equals 5t. Okay. Application. Okay. I needed to. Okay, now it works. Okay. Okay. So it's going to be 5. So s is an integral from 0 to 5, 0 to t, parameter tau, okay, and that's going to be 5t. Okay. So the relation between s and t is very simple. So, oh my God, something wrong with my. I don't know what's going on. I have to be very careful. I'm not going to touch anything. Okay. All right. Yeah. Let me just write down the. This is just equal to 5. Okay. Be very careful. I'm not going to touch anything. So the relationship between the arc length and the t is very simple. The proportional. So this t is going to be s over 5. Okay. Right. Now, so we got a new parameterization. So r over t, okay, you can replace t by s, right? Because t is a function of s range, right? So that is cosine 3t, so 3 times s over 5. That's how I did it actually. And the sine 3 s over 5. And it's 4 and s over 5. Okay, so that is a new parametrization for the same curve. Okay, and it's good, that this is, you can denote it by, yeah, you can denote it by r2 dot s. Okay, so that means it's cosine, 3s over 5, sine 3s over 5, and oh my God, so I should maybe, can I open, this is yeah, it says to be patient. Let me open it. Let me double check. Okay. If it's not open, actually I have to restart my computer for 1 minute. All right, let's try this. I got 2 files now. Nope, I have to, sounds like I have to restart the computer. I'll start normally, let me check. Okay, that works. Yeah, that works. Okay. All right, okay, that was a technical problem. Right, so you can get yeah, just denoted by is. Okay, then they're given by the above formula. Okay. All right, so we have so now I just show you it's always possible to find the parametrization with respect to arclengths, right? And assuming we have this nice parametrization, okay, and given curve, we can, yeah, I'm going to introduce the curvature, okay. We assume that this curve is parameterized by the parameterized with respect to arc length, okay. So R, okay, it is going to be, I'm going to use R tilde, okay, R tilde S, okay. So that means it's always equal 1. Okay. And this is unit vector. So in this case, T, okay, is going to be R prime T. Okay. So T is a function of S, a vector function of S. Okay. Now, this is a unit vector. So that means T S times Ts is going to be 1, right? Okay. And yeah, they're trying to use the same parameter. Let's make these simple. Okay. So now, when you differentiate, okay, use a product rule, right? Differentiate both sides, use a product rule. First of all, you have this fact, okay? Yeah, I'm not going to mention this parameter here, just T times T, okay, make it easier. So when I differentiate with respect to T, with respect to S, and I get, right? And then on the right-hand side, the derivative is going to be derivative 1 with respect to X is 0. Okay, so I get, since those two vectors can be switched the position, so you get twice of dt ds dot t is going to be 0. So what does that mean? That means, okay, if your parametrization is with respect to arc length, okay, so that means dt ds is perpendicular to t, okay, right? Okay, perpendicular to t. So if I draw the picture here, I get t here and another vector maybe in that direction. It's very short in this case, right? So this is a dt ds, okay? And it's guaranteed it's going to be perpendicular. And we notice that the length of that curve really tells you how curved of this curve at that particular point. And it's short, maybe more flat, and longer, then it's more curved. Okay, so I'm going to introduce the definition. Yeah, I'm going to introduce a terminology. Okay, so hey, at that point, dTds is going to be called the curvature. Okay, of the curvature of the curve at that particular point. Okay, depends on the point. Okay. Right. Okay. All right, so that is curvature. Okay. Now we continue. We can normalize this curvature. Okay. This curvature vector. So I can let because this is not necessary to be the constant length, right? So it changes, right? So I can normalize it, and I will get, yeah. Yeah. So we can get, yeah, and let the same time, I'm going to let n to be dtds divided by this. So you can have still have a unit length. That's n. Okay. So n and t have the same length. Okay, they're both equal to what? Okay. Okay. So then we have, okay. Now you have two unit vectors perpendicular to each other, right? So n is perpendicular to t. Now what you can get? You can get a third one in three-dimensional space, which is perpendicular to t and n. So then you let b to be t plus n. Okay? Then this is a unit vector also, it's called a binomial vector. The name is not important. But then you get this b as a length, it's a unit vector, and the b now perpendicular to t, and b also perpendicular to n. Okay, so you get three vectors. If you look at the picture again, yeah, this is a picture again. This is a t, that is an n. Then you have another one called the b. Okay, this is in three-dimensional space. Three vectors. Okay, so at every point, okay, we can get the frame. This is called the moving frame. Okay, because when the point moves around the curve, and this frame may be rotate. It's very interesting. Okay, the frame, then the frame rotates. All right. So our point is, if we are not given parametrization with respect to arc length, how can I do all this computation? How can I find the tangent vector? Okay. How can I find the tangent? How can I okay? How can I find the curvature? Okay, given an arbitrary parametrization, given okay. Okay, how can I do? First of all, tangent vector, I already know that t is going to be, right? The unit tangent vector is going to be dr dt, okay? No problem. And then divide by its length. Okay, let's use the d instead of prime, okay? It's better to use because we are going to have different parameters. So it's better to use d dt instead of just r prime. All right, so now, so this can be also viewed as a function of s, right? After you parameter. So you let S be the arc length. Okay, so that means S is going to be integral from A to, right? So at least we should have this dt equals, yeah, equal this. Okay, I'm going to use a d instead of r prime. Okay. All right, so that's the relationship, right? So now I'm going to differentiate dt and with respect to s. T can be viewed as function of s because t is going to be a function of s, right? And s is a function of t, you know, they're inverse to each other. So after you replace t by t over s, then this can be viewed as a function of t. function of S. But by the chain rule, okay, you have this, right? And you can put it in the denominator. Okay, you have this. Okay, so now you can compute it. Okay, so you can compute this. So this is a formula. You can and this length, right, tells you the curvature is going to be the length of this vector, right? And we can compute the curvature right now because you can just compute this two. Okay, and the denominator is nothing but okay. The numerator, you have this. Okay. So how do you compute curvature? You don't need to find S. Okay, you don't need to find the arc length. You just need to find you find the derivative of the vector function with respect to t. Then you normalize it. You get a unit tangent vector. Then you differentiate with respect to t. You take the length. Okay, find the length. That's the numerator. The denominator is just the length of the tangent vector of the original parametrization. Okay, this is the formula. But even this formula still not. It takes more time to compute the numerator. Okay, we probably can find a new formula, but before we do that, let's take a look at some examples. Okay, and this is yeah, let's take a look at examples. Okay, R over T. Okay, R over T, that is going to be, let's find the example. Okay. Okay, I still use my, yeah, I just use my same function, okay, make it easy. So cosine 3t, right? Sine 3t and 4t. Okay. So the derivative R with respect to t, okay, is going to be -3 sine 3t and 3 cosine 3t and 4. Okay. Okay. And okay, so okay, so this is going to be we already did as a find the length, right? It's going to be the square root of square root of each of the term, the square root of the sum of the squares of each component. Yeah. Okay, and I skipped some steps here. We already did the computation. Well, the pages go again. That's really, yeah, that's causing me big trouble. Yeah, and next time I'm going to restart the compute at the very beginning of the class. That helps. Okay, so we already find out this is a 5. Okay. Okay. So the tangent, unit tangent vector, this will be function of t, right? So this just r dr over dt, and then normalize it. Okay, so this is going to be 5, so it's going to be -3 over 5. You see 5 is outside, right? 3 over 5 is outside, that's not inside. Okay, so you can check. This is a unit vector. It's a function, right? It's a vector function of t. All right, now, according to our formula, right, I needed to find the derivative of capital T with respect to T, right? So sine becomes cosine, and the negative 3 times 3 is 9 over 5. And this will be 9 over 5 negative sine 3t. And the third term is 0. All right. So we have to find the length of this again. Okay. The length is going to be square root of a square, the sum of the squares of each term. Okay. So that is going to be okay. Now after you simplify, cosine square plus sine square is 1. So you end up with 9 over 5. It's also constant. Everything's constant. That's good. Okay. So the curvature at a particular point, according to our formula, is going to be this. Okay. So the numerator is 9 over 5 over 9. The denominator is a 5, right? Remember that. The denominator is 5. Right? The length of the tangent vector to each point is 5. Okay. So we end up with 9 over 25. It's constant. So that means the curve is curved evenly at every point, which is constant curve. So look at this curve, right? Look at this ellipse, right? So, but if you compare the two different points, there's no reason you can say they're different. They're curved evenly in the same, right, in the same way. So it's not a surprise if it has a constant curvature, right? It's not a surprise if it has constant curvature.
Is this a K?
Hmm?
Is this a K? The letter K?
Yeah, K. Yeah, curvature. Actually, in geometry, there's another quantity associated with this curve that's called torsion. I'm not going to talk about torsion. Okay, that tells you, the curve actually is also lifting right now. Okay, not only just rotate along the z-axis, it's also lifting, going up. Yeah. So that you have to find a way to describe that, right? Because this is like a spring, right, along the cylinder, and actually you can push the spring down a little bit, and you get a new curve. That new curve still has the same curvature, so there's no difference between these two curves, okay, over this cylinder, okay, and the difference between them is actually one is stressed, the other one is pressed. It's just it presses that downward a little bit. Okay, so there's another quantity that describe tells the difference of this two. Okay. The question is, should we always find the unit tangent vector first and differential with respect to t? Actually, it's not necessary to do that. Okay, we can try another. We can derive another formula. Okay, so see, t is going to be let's use r prime. Okay, t is going to be dr over dt. dr over dt. Okay, so using this formula, I can express it using, right? Then I differentiate both sides with respect to t. Okay, first of all, I have derivative of this bad part. That's okay. Then I have a, right? All right, that's good. So now I'm going to do, this is the bad part, I don't want it. How can I do that? Well, I look at the cross product. If a cross product, then T cross T is going to be 0. So actually what I get is this part, only that part. So that is going to be dr dt square and the T cross dtd. Okay. All right. And yeah. All right. So now what? Okay. We can take the length on each side. Okay, find the length on each side. But I needed to modify this a little bit. Okay. We know that this dt I can change the ds and then ds dt, right? Okay. And then this can be also, yeah, right? So this one, I remember that is just the derivative of the length, right? This is going to be dr dt, okay? So now you have a dr over dt cube. Okay. Since these two vectors are perpendicular, okay, so this is a t, that's a little dt ds. I know the curvature is going to be dt ds, okay, the length of that. So this length actually is going to be the length of t times ds and the times sine theta. So what is theta? Theta is there. But theta is already 90 degrees. So, and this is 1, and here's curvature, here's 1. So the length of this product, right, actually is going to be just curvature k. So therefore, I take the length on both sides, I get curvature, okay? So now I get another general formula. Curvature can be computed directly and bypass the unit tangent vector. All you have to do is just to differentiate the original arbitrary, the original vector equation. Okay, then you use that to find the cross product. We call it cross product, right? Find the dot, this product, yeah, product, right? And then find the length. Okay, so this is a function. This one tells you the curvature at the point of t. Okay, so the curvature function at that particular point. The curvature at over t. Okay, A is the curvature. Okay, so let's take a look at the example. So not curvature is not necessarily constant. Okay, this is a good example. I'm going to. Okay. Yeah. Okay. So let over t to be 1 t and t squared. Let's just take a look at this and no restriction on the t. Okay. I'm trying to find the curvature formula. right? Trying to find the curvature formula. So the first derivative, I don't need to find the unit tangent vector, okay? I don't need to find the arc length. So I get 0, 1, 2, t. Right? And the second derivative, I get 0, 0, 2. Right? Very, very simple. So the next step, when I needed to find the cross product, how can I find the cross product? I call it cross product. Then we have some different names. Okay. So this is another vector, right? And by definition, it's going to be ijk and 0, 1, 2, t, 0, 0, 2. Right? Then they expand this three-dimensional 3x3 determinant. So I is going to be 1, 2, t, 0, 2. This matrix is for I. And then you change the sign. 0, 0, 2, t, 2. Okay. And then 0, 1, 0, 0. Okay. And I find out only the first term is not equal to 0. Okay, it's going to be 2, just 2i. This is interesting. Just equal to 2, 0, 0. Okay. All right, so now I can write down the curvature. The curvature formula is going to be, right? Right? Yeah, for the convenience, I go back to just use our primer because I don't have a arc length here. Just t is the only is a variable. So when you use our primer means t is the only variable here you're dealing with. Otherwise, you don't know which variable you're talking about when you find the derivative. Okay. So the length is just 2, the numerator. The denominator, I have to look at our parameter. It's 1 and t. So it is going to be square root of 1 and 0 square plus 1 square plus 2t square. And then cube, right? So let's rewrite this again. I cannot simplify. All I can do is just express in this form. Okay. Now, what does this tell you? I think it tells me this is always less than 2, or less than or equal to. Okay. When t is 0 equals 2. Now, how does the graph look like? Okay. How does the graph look like? That's very important.
Do you mind explaining how did you get 1 plus 4t to the square to the power of 3 over 2?
Oh, sure. All right. Here's it. See, this is going to be 0 square plus 1 square plus 2t square, right? And then cube. So step 1, you get the 1 plus 2t squared is a 4t squared, okay? And the square root is actually 1 plus 4t squared into the 1/2. So
perfect, thank you so much.
Yeah, so we use this notation. Okay. Radical is just traditional notation. We get used to that. Actually, it's not necessary to use a square root. Okay. Here. Okay. So now let's go back to the function. Go back to the equation. Let's give me 1, right? I have a 1 and t and a t squared. How does it look like? Okay. It is actually the first component is always equal to 1. Okay. So you can draw a plane passing through this line. Okay. You imagine. Okay. So this is a plane perpendicular to the x-axis. So the curve must be on this plane. Okay. And y is going to be t. And the z is going to be t squared. So the relationship between z and the y is going to be z equal to y squared. So this is a parabola. Actually, it's going to be the parabola on the plane perpendicular to the x-axis. It looks like z equals y squared, so the parabola goes like that. Okay. Yeah. Imagine you have a plane perpendicular to a z-axis and parallel to the yz plane, and you have a parabola on this plane. Okay. And when t equals 0, you are here. Okay. When t goes to infinity, go in that direction. And look at the parabola, right? The curvature is going to be, so curvature, you see that the curvature when t approaches plus minus infinity, the curvature is going to be, the curvature approaches 0. Because, yeah, clearly it's 0. So if you fly along this parabola and go to infinity, you will see that the parabola becomes more and more straight line. Okay, straight line, the curvature is 0. You don't see its curve, but nearby the starting point, t equals 0, it is indeed a curve. Actually, the curvature is going to be 2 at that particular point. Okay, the curvature is going to be 2. This is the most curved point of the parabola. Okay, it's most curved parabola. Okay, now. Now you can also take a look at find the moving frame. You know, this is the t, and then I think this will be the n, and then the third one is a b. Okay, if I look at the picture, I think b will be the constant vector. Okay, it will be perpendicular to the plane. Okay, so from the picture here, I can tell. Okay, the t's keep changing, right? T keep changing. So that's how to find the t. Okay, the unit vector. Okay, we already did a computation. Capital R of t, right? R of t is 1 to t. So let's see. So t is going to be, so it's going to be 0, 1, 2 t, and this is going to be the length. So let me write down. It's a 4t squared. Okay, so this is a unit tangent vector. Okay, and to find the b is a little bit difficult because the b has the n, right? And remember how to find the n. N you have to find the n is going to be you have to differentiate, right? So this is yeah, okay, okay. So you differentiate that tangent vector. Okay, it's a little bit difficult. Okay, but I think before I find the b, you know, these yeah, this n is going to be t prime t. Okay, and the b is going to be t cos n. But I'm pretty sure from the picture, this is already clear that it's, to me it's a 1, 0, 0. Okay, it's a unit vector and perpendicular to the plane. Before I do the computation, I know the result already. So all you have to do is just differentiate the above vector. You will see that's pretty complicated. There's a denominator there, right? And the square root. Okay, so it's not easy to find this n, okay? And you have to find the derivative. But if you are patient enough, you can find the derivative. And let me just finish that within a minute, okay? And this is going to be 1 plus 4t squared to the negative 1/2. And I know that's a 0. Okay, the first term is 0. That's easy. It's already 0. So you all have to do is find the derivative of the second term. 2t, 1 plus 4t squared right? Then you differentiate, you get 0, and this one, you get negative 1/2 1 plus 4t squared, and the negative 3/2, and then you have 8t here because derivative of 4t squared is going to be 8t. And here you have to use a product rule. Okay, and plus it's minus 3t and times negative half, right? And then you have 8t. Then you simplify, okay? Let me just write down this answer here. And this one, we cannot simplify too much. And you have a negative becomes positive, and 2 cancels out. It's 8t squared. Okay, so this is a tangent vector. It's complicated, and then you normalize it, and then the n has and then after you normalize it, clearly the n has two components, something here, something here. So the n vector is actually, the normal vector actually lines on the plane because the first component is 0. So let's stop here, okay?